How you doing? I'm Mr. Rose, and today we're going to be discussing some of Newton's laws, specifically two Newton's laws questions that are pretty introductory. Now, this first one that you can see in front of you, you've probably already started reading and ignoring me, and that's okay, because I'm going to ask you to solve it again before you watch me, or before we discuss solving it, actually. The second one's going to be a little bit more in detail, but you can knock both of these right out of the park. So I'm going to pause one moment while you finish reading the question. Notice there's parts A and part B. I would like answers to both of these. All right, now that you've paused and you've solved this question, let's talk about them. Obviously, we have two forces acting. We have F1 and F2. There's part A and part B, as I said. And this one is so easy, I'm not even getting out of this chair to use that whiteboard. Not going to happen. We're going to solve it just through discussion. So the first one, we can see that F1 has a 3 Newton force and a 4 Newton force, both in the positive I and J notation. I do want to note that I couldn't give little hats on my computer screen. That should be the I hat and J hat notation. F2, we can see, has a negative 3 Newton force and a negative 4 Newton force. Well, wait a second. I can forget about the I's and the J's if I wanted to. You shouldn't. But if I just look at the I hat and the I hat, 3, let's see, I is the X, right? Okay, so 3 newtons that way and then 3 newtons that way, because remember, the negative in physics is just direction. Well, those two things are going to cancel out, and I get 0, which means the J, the 4 up and the 4, those two things cancel out, and I get 0. So the acceleration for part A is just 0 newtons. Look at that. No whiteboard marker, no calculator. Let's move on to B. Well, B, we have a lot of the same. We have a little bit of a similarity here. B, we have 3 newtons again that way and 3 newtons that way. Those guys cancel out. But in the J hat direction, or the Y direction, we have 2 4 Newton forces, which means I have 4 newtons in the J or up and 4 newtons up. Now I'm using a standard coordinate system since I didn't draw it on the board back there. So 4 newtons up and 4 newtons up are 8 newtons. So F1 plus F2 is 8 newtons in the J hat direction. And since my block is 2 kilograms, I just simply apply F equals ma. My force is 8 newtons in the J or the Y direction. My 2 kilogram block is 2 kilograms. Well, 8 newtons divided by 2 kilograms, 8 divided by 2 is 4 meters per second squared. So the answer to this one is 4 meters per second squared in the J hat direction. Told you, didn't even have to get out of this chair. Now the second one is a little bit more difficult. Again, I'd like you to take a moment and read this question, and we're going to get right into solving. All right, so you read the question, and there was a mistake that I'll point out that I wrote up here. As we go through the year, we're going to see that I solve some of these problems differently every time. Now, actually, one thing that is cool about physics, I'm going to move this so it's a little bit straighter. Oop, that's more crooked. All right, well, you know what? That's just how it's going to be. Is there are multiple ways to solve problems. That's not what I mean here. What I mean here is you see a whole blank board in front of me. You may have also seen some videos where I had a whole bunch of stuff already written. So videos like this will take a little bit more time, but it gives you the opportunity to keep pausing. Go ahead, come back, how'd you do? Do you understand? Instead of just seeing everything already solved out in front of you. So like I said, it will take a little bit more time. I have a summary of our question up here, and I'll point out the mistake as I realized when I wrote it on the board. Here I have my equation of motion. X of t is 3.0 m, 4 meters per second times t, ct squared minus 2. This should be meters per second cubed, and not meters per second squared, times t cubed. Now, how did I know that when I read it? Because I didn't do this yet. I knew that because of dimension analysis. What that means is we can use dimensions or units to figure out the direction we're supposed to go. Like, does my answer make sense? So, for example, if I said at the given information at t equals 3.0, that doesn't say 30, that says 3.0 seconds. F is equal to 36 newtons. We're looking for C. So at 0 seconds, well, let's see. 0 times 4 is 0. 0 times C is 0. 0 times 2 is 0. I have x, which is a distance or displacement, equals 3 meters. Those units make sense. Well, and if I had a time, right? Well, let's see. I know that means that meters per second times seconds, those seconds will cancel left in meters. This is seconds squared, so C must have a unit of meters per second squared. And here, meters per second cubed, in order to be in units of meters, then I need to have a seconds cubed on the bottom. So that's dimension analysis. Anyhow, we are trying to figure out what C is. I just told you that C must be in a unit of a meter per second squared. Well, I've got a force, I've got a C in meters per second squared. That must mean I can use this orange marker to write F equals MA. And I'm super excited because I'm at F equals MA, and it's awesome. But that's actually not even helpful a little bit. I can't even come close to using this. So, Mr. Rose, like, what are we doing here? Are we doing kinematics review in Newton's? We are doing kinematics review in Newton's laws. Wow, you sly little devil. Why would you do that? I'm going to do that because these are concepts that keep coming up and coming up and coming up. And we're going to have to keep working with them such that they become like secondhand nature. So what are we given? Let's see. How do I get to this acceleration? Right? What am I going to do here? Oh, I remember. I remember that if I take some derivatives, I can get from displacement to, I can get from displacement all the way to acceleration by taking not one but two derivatives. So I say often my notation is a little scratchy, and I'm trying to keep things to this one board. So if my notation is a little bit off, I do apologize to that. But I know I'm going to take the first derivative of this x of t. So the first derivative is velocity, and I know that by definition is dx dt. Now I'm going to do this in my head, but I'm going to do this with you. This is the derivative of x with respect to t, so I'm taking the derivative of that whole function with respect to time. Let's do one thing at a time. The derivative of 3.0 m, there is no t there, so that's just a 0, plus the derivative of 4 meters per second t. Well, the derivative of t to the 1 is t to the 0, so that means I'm just left with this 4.0 meters per second. Now, the derivative of ct squared, well, let's see, I know t squared, the derivative of t squared is t to the 1, so then I have plus ct, and then I have minus the derivative of 2.0 times t cubed. Oh, that one's confusing. T cubed, derivatives. Okay, so let's see. 3 minus 1 is 2. So it's going to be something t squared. And then, okay, wait, the cheat, I have 3. Oh, man, wait a second. So this is t squared. So is it t squared times 2? So is that 4? No, wait, I remember the derivative rule. Okay, it is this exponent times my coefficient, so 3 times 2 is minus 6.0 meters per second cubed times t to the 3 minus 1 is t squared. Now, did you see what I did there? There's a mistake on the board. Are you saying, yo, Rose, what are you doing? Or did you catch the mistake? The mistake was here. Remember, a lot of people fall in this trap at the beginning. This should be 2 times the coefficient, so my coefficient is 1, and then to the t to the 2 minus 1. So this isn't ct. Where is my eraser? There's my eraser. Don't fall into that trap. I'll even put it back in my orange color. This should be plus 2ct, because again, it is that coefficient times, that exponent times the coefficient. 2 times 1 is 2ct to the n minus 1, so we have 2ct. Now that is my velocity expression. Now I need to get to F equals ma because I'm given this force, right? So I'm still trying to figure out what that is. So now I'm going to do one more time the acceleration with respect to time. That is dv dt. And I'm not going to put in the zeros this time. I think we got that. So this is obviously 0. The derivative of 4 meters per second, there's no t there, so that's also 0. So now I have the derivative of 2ct with respect to t. That's just 2c minus 2 times 6 is 12.0 meters per second cubed. And then the derivative of t squared, again, that was that times that is 12. N minus 1 is just times t. And here we can do that dimension analysis thing again. T is in seconds, meters per second cubed times seconds and meters per second squared. Perfect, because acceleration's in meters per second squared. So now this is something that we may not have done before. This is my acceleration. So what the heck am I doing with that? I'm actually going to put this right into my acceleration. It's my F equals ma, right? That's what I can do. I was given, I got to look back, I think it was a 2 kilogram block. So, dropping things on the floor. I say F equals ma. F is 36 equals my 2 kilogram block times my acceleration of 2c minus 12.0 times t. Now again, I skipped a step. What did I do? I knew this is 36 newtons at t equals 3 seconds. So to be fair, my general expression should be this. And now I can say, I'm going to just do some math in my head. If I put in the 36 divided by 2 is 18. So I'm going to have 18 equals 2c minus 12 times 3. I can do a little bit of math, or I can use my eye. I'll just do the math out. And we get c equal to 9 meters per second squared. So we had a direct application here. Newton's laws rolling right into kinematics with some calculus review. That's all I got for you today. Please feel free to like, comment, or subscribe. And we'll see each other next time.